Why didn't I think of that? Thank you, Ian, so much.
No.
All ready to go?
Still should be working. Right, have fun, guys.
Thanks, Ian.
And right, Nita, John.
Nita, what's she got to do with it? Right, guys, sorry about that, but I think we're up and running now. Let's go back. Picking up from the last lecture, we were looking at multi-layer perceptrons, and perceptron is a word which McCluskey and Papart, a couple of Americans, invented for the McCulloch-Pitts neuron. So it's the same neuron model. It's McCulloch-Pitts, but this new word perceptron has been coined by them to describe it. We're looking at a two-layer structure, and we're looking at the XOR problem, because this is a classical problem that a single neuron cannot solve because it's a linearly inseparable problem. So we have inputs A and B. These boxes are complete neurons, so they've got weights inside them, they've got the summer, they've got the bias, and the output threshold. Neuron 1, neuron 2, and neuron 3. Now, because it's the exclusive OR function, I'll draw this again alongside it just to remind you, we can plot it out in two-dimensional space, A and B, and the values in binary are A is 0 and 1, and B is 0 and 1. I can now plot on that the output F terms when F is 1 for the XOR, and it is going to be 1 when A is 1 and B is 0, or A is 0 and B is 1. For the other two problems, the input patterns, 1, 1 and 0, 0, F is 0. So if I draw these in blue, and if I draw these in red, you can see there is no single line, no decision surface, and a bias will allow us to have the decision surface that doesn't go through the origin. But if there's no bias, if there is a bias, we can have the decision line, a straight line in any position. And the best we can do is have one of the patterns incorrect. So if I now draw the decision surface here and have this the plus side and this the minus side, and F equals 1 is the plus side, this will be correct on the plus side, F equals 0 on the minus side correct, F equals 0 on the minus side correct, but this one would be an error. So it will partially solve the problem, but with some error in one of the input patterns. If I now take the second neuron, again the same input, and I put a decision surface in this position here, again defining above as minus and below as plus, this pattern will be correct, 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 and the error is there. Now, in our structure, those two neurons are transferring A and B, and we get D1 and D2 outputs going into a third neuron. Now, take the decisions from neuron 1 and neuron 2 and plot them for neuron 3. And I'm describing the dimensions as plus or minus. If I were to put a threshold on it, it would be 0 and 1. So it's still binary. Now, having a look, the F equals 1 pattern, which is A is 1 and B is 0, is on the plus side of D1, and it is on the minus side of D2. So it will be plus for D1, minus for D2, and this F equals 1 pattern goes to there. For the two F equals 0 patterns, they are a minus output for D1 and a minus output for D2. And those two patterns, which are different in AB space, will coincide in the hidden space between the neurons. So those two patterns come together. And finally, F equals 1 when A is 0 and B is 1. It is negative for D1, and it is positive for D2. It will be negative for D1 and positive for D2. It will be that pattern there, and that will be the f equals 1 pattern. And lo and behold, we've solved the problem, because now in the input space for neuron 3, it's linearly separable. D3, which is this decision surface, let's define that as being positive on this side and negative on this side. F1 is correct, F1 is correct, both positive, and the two F0s are both negative. We have solved the XOR problem. Now, just to show you that weights will exist to do this, if I take the first neuron and plot the patterns going into this neuron, A, B, and include the bias, I will have 0, 0, 1, 1, 0, 1, 1. Those are the inputs for XOR. The bias is 1 for all inputs. And the class for neuron 1 is 0, 0 is negative, 0, 1 is negative, 1, 0 is positive, and 1, 1 is negative. So 1, 0 is positive, 1, 0 is positive, and the others are negative. Now we need a weight vector to give this decision for these input patterns. Now you could use a training algorithm, the fixed increment, but because it's such a simple problem, we should be able to use logical reasoning to solve the problem. Now, looking at these three input patterns, including the bias input, the very first pattern here, 0, 0, 1, it has to have a negative scalar with the weight. So a possible weight, or an essential weight for the first pattern, the bias weight has to be negative. Choose a negative value, let's say -4. Right, so with 0, 0, -4, we will get a negative response for pattern 1. Now look at the positive response. Weight W2 is being multiplied by 0, so that can't affect the output. Weight W1 is multiplied by 1. Weight of the bias is multiplied by -4. This has got to be more positive than -4 is negative. What shall we say? Let's try +5. Right, so we've still got 0 in the middle. So with the weight so far, assuming 0 in the middle, we've got negative correct, we've got positive correct, and for this one, we've also got to get a negative response. So let's say -2. So again, a potential weight vector. Scalar with the first one is going to be -4, correct. The scalar with this one is going to be -2 plus -4 -6, negative, correct. The scalar with this one is going to be +5 times 0 times -4 plus 1, correct. And finally, will it work out? This has got to be negative, +5 -2 is +3 -4 -1, correct. That is a weight vector that solves the problem. And it's one of many. Can somebody looking at that tell me another weight vector that would solve this problem? Give you 10 seconds. Some questions coming in. How do the classes get assigned? It's for you to decide which is positive or negative. It's just a label. Right, another weight vector. Just guess, just using logical reasoning. Well, the obvious one would be +10 -4 -8. Let's have one that isn't a logical multiplication of the original vector. Let's have -3. What shall we do? Got to have this one plus. Let's have +4. And what should we have in the middle? The last one's got to be negative, -2. Just check if that works. It is going to be 0, 0, -3, correct for the first one. For the second one, it is going to be -2, -3, -5, correct. For the next one, it is going to be +1. And for next, so there's another weight vector. And there are many weight vectors that will solve the problem. Now my conversation has just gone off on my other machine. Oh, isn't this technology awful? Right, I'm back there. Right, that's for neuron 1. Let's now have a look at the weights for neuron 2. And for neuron 2, the inputs are going to be A, B, and bias. And it's going to be 0, 0, 0, 1, 1, 0, and 1, 1. There's always 1. Right, and the classes we want, if we refer back to the two-dimensional diagrams for the second neuron, it is going to be class, it is going to be minus, plus, minus, minus, and the same with logical reasoning. I think a weight vector that will solve the problem is -4, +4, -3. Just do a quick check. Negative, positive, negative, negative. And finally, for the third neuron, oh, why is my screen frozen? Machine is particularly slow. Ah! Now for neuron 3, because the two negative patterns both go to the origin, we only have 3 possible inputs. This is the data that occurs on the hidden layer. It will be 0, 1. It will be 0, 0 for the two negative patterns and 1, 0 the positive. So the bias is 1 for each of those. And the class is going to be 1, plus, minus, and plus. And again, simple reasoning, take the middle pattern, it's got to be a negative. Let's put a negative weight in, -4, say. For the top one, it's got to be a positive scalar. So the weight of the first element has got to be more than 4 in magnitude, let's say +5. And for this one, same, let's have +5, +5, 4. So there are 3 weight vectors, 1 for each neuron. It will solve that linearly inseparable problem, which is interesting. And it leads us to the need for multi-layer systems. Right. Now from there onwards, if neurons can perform an exclusive OR function, what other logic functions can neurons perform? Well, it turns out that the exclusive OR is the only 2-input logic function that needs a multi-layer perceptron. All the other logic functions can be separated by a single neuron, because the other functions, apart from XOR and its complement, which is XNOR, all the other functions are linearly inseparable. So let's take and. Oh, stop it. Ah! Stop playing up. Oh, I've lost my whiteboard. The response today seems to be extremely slow. Can anybody see anything coming through? Pinch to zoom, it's appearing completely dead. No, it's frozen. It's not my day today. Oh, dear, dear, dear. No. Somebody else has got something working on the message. It's too faint, really thin. I've got nothing here at all. My whiteboard has given up. Okay, what are we going to do? Let me try and talk you through some ideas. Using a neuron for an AND gate. Now, what you need to do is to plot the AND function in two-dimensional space, the same as we did for the exclusive OR neurons. So you will have A and B on the axis, and for the AND function, you will have a 1 at point AB equals 1, 1, and for the AND function, allow. Stephen is requesting allow. I'll press the allow. No, nothing coming through. Let me try zooming in, Stephen. Do try. 0%. SB come up. It's not even responding to the pens now. Try zooming out. No, doesn't work. Just tried it with remote control. Okay, let me carry on talking. Prove to yourself that the AND function is linearly inseparable. Draw a two-dimensional graph, vertical axis A, horizontal axis B, and the values on A are 0 and 1, and similarly on B, 0 and 1. The vector point 1, 1, AB equals 1, 1 for the AND function corresponds to F equals 1. The other 3 points are F equals 0. Looking at that graph, you can see that there is a line, a straight line, a decision surface you could draw, which has the AB equals 1 point on one side, call it the positive side, and the other three are on the negative side. And you could devise weights, and you need a bias because there's a pattern at the origin, AB equals 0, 0. So for the three inputs, AB and the bias, you can devise weights which will perform the AND function. Now, what is more important is the NAND function. Now, if you do the same for the NAND function, no, still can't go out, come in. No, 200% coming in. No. No, I'm giving up on the whiteboard. It just doesn't work today. Right, so the AND function is linearly inseparable. Now, so is the NAND function, because the NAND function is the inverse of the AND. So on your AND diagram, all you've got to do to get the NAND function is convert the ones f equals 1 to 0, and f equals 0 terms become ones because it's the inverse of the AND. That function is also linearly separable. Now that's important because you should know from level 1 logic, the lectures in level 1, that NAND is a universal gate. So if you have NAND gates, you can build any digital system. If a neuron can perform NAND, then you can build any digital system out of these neuron models. And 30 or 40 years ago, this was thought to be a possible new way of designing logic. And the same device, which we're now calling a perceptron, was called threshold logic, TLUs, threshold logic units. And that is very rewarding and reassuring to us, because it means any digital system, if you design it, it can in theory be built by NAND gates. And if it can be built by NAND gates, it can be built by neurons. So it does give us the potential of building all computing using neurons, providing we could train the thing and providing we can get the right structure. Now, structure is hugely important. And if you're using a neural network simulator, you'll go into the system and it will ask you how many inputs. That's usually obvious. That's depending on the data. If it's a 3x3 digital image, or in the case of our example with the 4 pixel images, it would be 4 dimensions. The number of nodes you want on the first layer has to be determined, and the number of layers you need has to be supplied. Now, where do we get that information from? Well, going back to logic, you know that any system can be built in a canonical form, and the canonical form, excluding inverters on the inputs, is a 2-layer structure. So we can deduce from logic design that neural systems, in principle, need only 2 layers of nodes, or 3 layers if you include the inverts and the buffers on the inputs. So I call it a 2-layer system, but 3 layers, some people call it a 3-layer system. And the middle layer is the hidden layer. Now, depending on the function you're trying to learn, that will determine, hello, what's come up there? Oh, pretty good, yes. That looks like it, George. Excellent, cool, great. Right. From logic design, we know that canonical forms exist. So any system could be a 2-layer system or 3 layers, including the inverters. But you also know from logic design that there might be better circuits which are more efficient, which have more than 2 layers. And that was coming from cellular logic. Now, I want to give a challenge out here now. We've done the XOR function and we've seen how that can be implemented using neurons. What about 3-bit parity? Gosh, I'm writing now. It's started to write. Can you see this? Can you see the screen? It's come back to life. Great. 3-bit parity. Right, supposing I want to learn 3-bit parity, I'm going to have inputs A, B, and C. I'm going to have an output node, and this circle is a complete neuron, producing my output F. And I need how many nodes in the first layer? It's alive, yeah. This machine is intelligent and it's malevolent. It doesn't want to work for me. Beware of artificial intelligence taking the world over. Right. How many nodes would you put on the front layer? It's a simulator. It's asking you for your inputs. We went 3 inputs. We need 1 node on the output layer. How many in the middle? Give us a number. 2. Right, so the proposal is we have 2 nodes on this layer. There we are, and these are complete neurons. They contain weights, summers, and everything. So dunk, 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 dunk. Here is your hidden layer, D1 and D2, and that would be the structure proposed. Now, the sad news is that I know, because I've seen this problem before, that that will not work. We in fact need 4 nodes, 4 neurons on the input layer. Right, and if we had 4 layers, we could devise weights and it would work. So here is a challenge. Let's go away from toy problems and try and learn a real problem. What about a 16 input, a parity network? Right, we have inputs A1 down to A16. We're going to have a single node on the output, giving me F. So those are my inputs. The question now is how many nodes, for this to work properly and actually solve the problem, how many nodes on the input layer? 17, somebody says. Bit higher. Come on, let's have an estimate higher. 32. You're going in the right direction. No. If this was the lecture theatre and I was giving out packets of crisps, the 100 would be the closest, but not good enough. 64. I'll put you out of your misery, and this will come as a shock to you, but you have actually seen this before in logic design. You would need 32,768 nodes for it to work perfectly. Damn, yes, indeed. Now, why? For a simple 16 input problem, if you don't understand what the neural networks are doing, nobody would even suggest we need anything like that. 128 or 1,000 might be over the top. Now, where does that number come from? It's because for given functions, you need a certain structure to support them. And if we go back to our logic design of parity, that doesn't matter whether it's odd or even. Remember, if I go to a K-map, remember the K-maps? It gives me an opportunity to say 0, 0, 0, 1, 1, 1, 1, 0. Let's take a... Oh, go to the 3-bit parity, because that's the one I did before. Let's just Oh, let's get rid of that. Oh, come on. Oh, forget about it. It's locked up again. Oh, it's come back. Gosh, it's so slow today. It is incredibly slow. Can't even erase that. It's locked again. Damned. Come back. Now please work. Got rid of it, right. 3-bit parity. Oh, it really isn't me this time. The machine is just going so slowly. Can't even bring the pen up. At any rate, I'll carry on talking. Maybe the screen will come back in 10 minutes. Remember in year 1 when you were designing parity, the exclusive OR is effectively the parity of 2 bits. If you design the odd parity of 3 bits ABC, you found that on the K-map, the function did not minimize. And we ended up with 4 terms that wouldn't loop. That gave rise to 4 gates, 4 AND gates, and they couldn't be simplified. If I went to 4 inputs on a 16-bit K-map, 4-input K-map, we found that there were 8 ones. And so for 4 bits parity, we need 8 functions on the first layer before we OR them together. And if you take n inputs, work it out, you will have 2 to the power n minus 1 inputs, nodes on the first layer. And for n equals 16, that becomes 2 to the 15, and that is 32,768 nodes. So, unless we know the problem, the nature of the problem, we can't specify the architecture that will support the function. And the whole thing is for the system to learn the function. So we need to know what the function is before we can specify the network to learn the function. It's a bit of a closed circuit, and we don't have an easy solution to that. And I suppose in nature, the solution is redundancy. Because if we are trying to compare these neural networks to what goes on in nature, take the human, for example, we are playing around with not 32,000 cells, we're playing around with 10 to the 11 cells, 100 billion cells. And of course, a large system can perform a function. If you want a 2-input AND function, you can use 1 gate with 2 inputs. But if you used 1,000 gates, you could connect them up in parallel, they would still perform the single 2-input function. So larger systems with redundancy can support them. But you also know that a cell design will possibly, in the case of parity, it's quite dramatic, simplify the design of the problem. And for a 16-bit cell parity generator, look it up from level 1, you only need 16 2-input gates, but they are in 16 layers. And the idea of having a multi-layer system in neural networks is the idea of deep learning, where you do a decision on part of the input space. You then take that partial solution and combine it with more data, and you go through a chain of events with multi-layer networks. And of course, the training of the weights on those and the minimizing the error becomes slightly more tricky. Now, I don't want to go into deep learning in any further detail than that, but that is the way forward. So the final thing, hello, missed that one. The final thing I want to talk about on this section of neural networks is another application. Yep. Okay, yes, I'm struggling myself to interpret it without visuals because I can't write at the moment, but I'll try and go over that. We'll try and have a seminar next week and recap on some of these ideas. But the last thing I want to introduce on this particular topic is another application. It's writing again. But it's still not bringing up the controls. Gosh. No, forget about that. Maybe I can write a little bit. Yes, gone. Right. No, it's not logic. Neural networks to learn the function of a system. Now, so far, what we've been doing is using neurons to partition inputs into two classes. And the neuron model is only a two-class classifier, the plus class and the minus class. If you wanted to use it for face recognition, the two classes would be the plus class, and all the other faces would be the minus class. Now, with neural nets for function approximation, we are trying to model the function of a complex system. And the idea is that the decision surface becomes the function. So we have a network and we train it on the patterns which represent the condition of, say, a plant or a system that's working. And we train it so that the system, when it is working normally, is giving a zero output. And a zero output means that the inputs are landing on the decision surface. Now, the first thing to realize with this approach is that the single neuron is only linear. And linear systems are quite simple. For complex systems, we will need multi-layer non-linear neural models. However, let's get the idea over. Training. The training algorithm is for function approximation. Oh, how did that come up? It's similar to the error correction feedback, but it differs in one important respect. First of all, choose W, a random starting weight. First training pattern. Calculate W dot I, the scalar product. And that equals S. I'll go up. Right. If S is equal to 0, And this is going to be very unlikely. Oops, come back. It is unlikely that a random pattern will be on the decision surface. Oh, I've lost that now. If S equals 0, do nothing. Right, I've got 5 minutes to finish this off. If S is not equal to 0, update W. And the update is the same as we had with error correction feedback. An updated vector W prime equals W plus Ci, a fraction of the input pattern. And the update is such that W prime dot I, the updated weight vector with the current input pattern, forget about that, I don't know where that came in, must equal 0. Oh. Delete. Oh, it's a nightmare. I think we should all meet up at the pub and be socially distanced and have a face-to-face. I've lost it. I'm rapidly running out of time, folks. But I will think I better stop there, and I will go through this training algorithm for function approximations. Somebody said it would be perfect if I stopped. Yes, silence is better than the lecture that's been taking place today. Sorry about this, folks. Yeah, the pub, okay, yes, the pub, a good idea. I am meeting somebody on socially distant space. I'm in the university today after this lecture. If anybody wants to come and have a chat on one of the landings, if you're on campus, then you'll be most welcome. And we'll try and see if we can get better whiteboard facilities next week. And unfortunately, I'm afraid I'm lecturing to you on Monday again. Okay, guys, sorry about the nightmare, but we will.